Charles Darwin was a big fan of billiards. He loved his billiard table. It was one of his prized possessions and one of the most valuable things he owned. Well, not actually the table itself. In fact, it was the balls that were so valuable. Pure ivory carved from the tusks of elephants. Only the wealthiest could afford a full set. Luckily, he was married to an heiress. A full set of 16 billiard balls would require at least one, possibly two full elephants worth of ivory. The idea that any bar in the world might contain a billiard table available for anyone to play and not like run out of the bar with your pockets full of valuable ivory would have sounded insane in 1850. And the billiard industry was well aware of this problem. Billiard balls were getting more expensive. Elephants were getting more rare. It was thus not with an environmental motive that in 1867 the Felon and Colander Pool Supply Company offered $10,000 to anyone who could come up with a substitute material that worked as well as ivory but could be produced more quickly and sustainably than dead elephants. An inventor named John Wesley Hyatt took on that challenge. He used nitrocellulose, a flammable solid created by mixing cotton with nitric acid to create a hard, shiny white sphere. The properties were extremely similar to ivory billiard balls. The company never gave him the prize, but he did patent the technique, using it to create billiard balls, piano keys, and even teeth, becoming pretty dang wealthy in the process. Also, he pretty much created the industry that made all of the polymer materials that surround you right now, and that we'll be discussing today in Crash Course Chemistry. Also, elephants didn't go extinct, so that's a plus. The polymer that John Hyatt worked on was somewhat unsurprisingly kinda crummy. It worked well once it was created, but the manufacturing process was dangerous because nitrated cellulose can explode in a warm breeze. So luckily, some replacements started creeping in. Replacements with names that you probably recognize, like polyvinyl chloride or PVC, Bakelite, polystyrene, polyester, and nylon. These are all polymers, huge chains or sometimes three-dimensional networks of repeating organic units called monomers. Each polymer has a monomer, but they're all relatively simple at that basic one-unit level. The trick is that they can bond to each other on each side, potentially forever, though in reality the chains are sometimes hundreds, sometimes thousands, sometimes hundreds of thousands of units long. In order to make a polymer, all you need is a molecule that can easily bond to another identical molecule at 2 points. And the simplest of those is ethene, also known as ethylene. Its polymer, you'll be unsurprised to hear, is polyethylene, which you've probably heard about. We'll talk more about the specifics in a second, but basically because pi bonds in the double bond are weaker than sigma bonds, they can be broken and new monomers can be added. Just a note to avoid confusion, polyethylene has that "ene" sound in it, right? But it's not an alkene because all of those double bonds get broken to form new sigma bonds. It's a polymerized alkene, but the molecule itself is an alkane. It's confusing, so I thought it was worth pointing out. Now, chemists might want a bunch of different things out of their polymers. Maybe they want it to be stretchy, maybe strong, maybe transparent, maybe recyclable. Polyethylene is transparent and thermoplastic, meaning it can be melted and reformed, making it recyclable. Some other polymers, like polyurethane or Bakelite, are thermoset, which means that they change chemically during some kind of curing process and cannot be melted down and reformed. Polyethylene can actually be converted into a thermoset polymer by introducing cross-links, basically molecular bridges between those polymer chains. Any plumbers out there probably have heard of cross-linked ethylene or PEX pipe, which is what this is. It's extra super strong because of those cross-links. Polyethylene is also nice because its strength can be varied by changing the size of the molecules. If they're allowed to polymerize until they're tens of thousands of monomers long, the plastic they will form will be all knotted up in these ultra-long chains and it will be extremely strong. That's why this HDPE, high-density polyethylene, is a strong bottle, whereas this is much squishier. This is low-density polyethylene. However, those ultra-long chains also make it much more viscous when heated and thus more difficult to process. It also loses some of its opacity and becomes more of that milky white color. Now, polyethylene is great. It's really great. So great that it's the most common plastic in the world. We produce over 80 million tons of it per year. But we want a lot out of our plastics. Strength, color, elasticity, resilience, recyclability. We need everything from saran wrap to car tires. All of these are traits that chemists worked tirelessly to create in the early and middle 20th century and continue to work on even today. One of the earliest techniques that they used to try and bring out new properties was to change the substituents on the ethylene monomer. Just see what would happen. Like, what if we swapped out one of the hydrogens for chlorine? Well, you get polychloroethene. Kinda. That's not what we call it. Okay, so remember how benzene, when attached to a chain, is a phenyl group, and how those two words have nothing to do with each other? Well, the same goes for the ethene functional group, which is called a vinyl group. It's an old word, super old. It comes from the Greek word for wine. And that is why chloroethene is more commonly called vinyl chloride, and polychloroethene is more commonly called polyvinyl chloride, or PVC, which is what this little ducky is made out of, and also what records are made out of, which is why we call them vinyl. Now, what happens when we change out a hydrogen for a methyl group? Well, then suddenly this molecule is a propene, or if you're using the old ways, a propylene. And yes, if you polymerize it, it becomes polypropylene. If one of the hydrogens is replaced with a phenyl group, well, that chemical was first derived from trees in the styrax family, so it's called styrene. Polymerize it, polystyrene. Make a foam out of it, styrofoam. Now, if you change all 4 of the hydrogens on the base ethylene with fluorine, it becomes tetrafluoroethylene. Polymerize that, and instead of hydrogens, that polymer is bound entirely to fluorines. Fluorine, as we could guess from its spot on the periodic table, loves electrons. It is extremely electronegative. But because it holds on to its electrons so tightly and is so satisfied in this polymerized chain, the electrons are unavailable for even minimal interactions with any other molecules. I'm not just saying this stuff is super difficult to react with or it's really stable. It's more than that. The electrons aren't even available for the sort of interactions that make things stick to each other or cause friction, which is why you have heard of polymerized tetrafluoroethylene, because it's super useful either by its abbreviation, PTFE, or by its brand name, Teflon. So how do we actually make these things? Well, ethene-based polymers form through a process called addition polymerization. The monomers are simply added together and no byproducts are formed. In order to get the process kicked off, you have to introduce a free radical. To me, that always sounded like some kind of crazy freedom fighter diving into battle without much thought for what would come after he was consumed in the firefight. And that's kind of what they are. Free radicals are atoms or ions that have a single unpaired electron. This is crazy unstable. It's basically like having half a covalent bond dangling off the atom. Anywhere this can form a bond, it's going to form a bond. And in the case of addition polymerization, it attacks the double bond and joins with one of the carbons, while the other carbon is itself left with an unpaired electron. The molecule itself is now a newly formed free radical. It attacks another nearby pi bond, joining with another molecule of ethene, forming another radical. This process continues until 2 radicals meet each other, consuming both free radicals without producing any more, thus ending polymerization. There are, of course, other sorts of polymerization as well. Sometimes a hydroxyl group from one molecule is happy to join up with a hydrogen from another, forming water. The water will break away as a byproduct, leaving the 2 molecules bound together. This often occurs when an amine group with its loosely held hydrogen meets a carboxylic acid with its loosely held OH group. This is just what happens when hexamethylene diamine meets adipic acid, forming another branded polymer, nylon. By dissolving hexamethylene diamine and adipic acid into two different immiscible or unmixable solvents, we can actually create nylon right here. The nylon forms at the interface between the two immiscible liquids, and we can literally grab it and pull it out of the vial, twisting and spooling it until we get a nice glob of nylon. This works because hexamethylene diamine has an amine group on each end and adipic acid has a carboxylic acid on both ends. Thus, when the two-monomer unit, called a dimer, is formed, there's still a carboxylic acid on one end and an amine group on the other, allowing for further polymerization. These amine acid condensation polymerizations also allow for the creation of possibly the most important polymers on the planet. Natural polymers being created inside of you right now out of monomers that we call amino acids. Did you see that one coming? Amino acids polymerize through condensation reactions guided by the code in your DNA and some very complicated enzymes to form basically you. Other important polymers in your body include polysaccharides, which we use to store energy, and DNA and RNA, which we use to encode information for the formation of proteins. But that would be back to biology, which is a whole other crash course, which, to be clear, is available if you'd like to watch it. And thank you for watching this episode of Crash Course Chemistry. In it, you learn that the first commercial polymer ever saved the lives of a lot of elephants, that ethene is sometimes called ethylene, and that a huge variety of polymers is based on the addition reaction of ethene-based monomers, including Teflon, which is so frictionless because of fluorine's extreme electronegativity. You also learned how addition polymerization reactions work, and that other polymers are formed by condensation reactions, including the polymerization of amino acid monomers, which, along with other polymers like DNA and RNA and glycogen, make up a lot of the stuff that is you.